Hello everyone. In this video, we're going to do the same problem that we did in the last video. We're just going to use energy and energy conservation instead of Newton's laws. So we have a hoop, a disc, and a solid sphere rolling down an incline of length 2.4 meters and at an angle of 35 degrees. Now, this is going to be perfect rolling, okay, and that's key. All right? It's key from an energy perspective because perfect rolling means static friction, right? It means that the bottom of the hoop, disc, or sphere is at rest with respect to the surface, and therefore you have static friction, and static friction doesn't dissipate any energy. So we'll have no E-dis as part of this problem, which makes it doable. Okay? So, we're going to start out, part A here is we're going to figure out the velocity of each one at the bottom of the incline. So they roll down the hill. Okay, now I want to know what's its velocity when it gets to the bottom. First, a little geometry. I'm going to call the length of the incline here L. All right, in my problems, I'm going to work symbolically. And like in the last video, I'm going to work generally, right, until the very last moment, and that's when I'm going to address the difference between a hoop, a disc, and a solid sphere. All right, so we're going to be as generic as possible. Now, since we're doing this from an energy approach, obviously one of the storage mechanisms here is gravitational potential energy, in which case we need to know yi, the initial height the hoop, the disc, or the sphere starts at, not the length of the incline that it rolls down. Well, as you can see in the diagram, right, that would be yi. Little quick geometry, yi would be L sine theta. Right? L is the hypotenuse, so L sine theta will be yi. This is a substitution we'll make a little later on. So if we make our system, the hoop, disc, sphere, the incline, and the earth, right, it is an isolated system, and therefore the total change in the internal energy is 0. Since the ball changes speeds, the kinetic energy will change. Since it changes heights, the gravitational potential energy would change. There's no change in EE because there isn't any. There's no change in E-dis because, again, perfect rolling, static friction, no dissipated energy. So we have a change in EK and a change in EG. Every change in is a final minus an initial. Now at this point I like to cancel out anything that's a 0. Well, the disc, hoop, sphere starts at rest, so EKI would be 0. No kinetic energy to start out with. And if we call the bottom of the incline our 0 height, then EGF will be 0. And so we very simply get that the final kinetic energy is equal to the initial gravitational potential energy. And, you might have been able to jump right to this step if you thought it through, right? Or, of course, we could also draw an LOL diagram, but on an AP test, they want to see math. Now we've got to plug in expressions for this, and this is where we need to be a little careful. These are rolling down an incline. So we need to use rolling kinetic energy. And remember, something that is rolling is both rotating and moving translationally, meaning moving linearly. And so rolling kinetic energy has a rotating part and a translational part. 1/2 I omega F squared is the rotational part of the kinetic energy. 1/2 M VF squared is the translational part of the kinetic energy. And then EGI is, of course, MGYI. Now, be aware that this V is really the speed of the center of mass, right? That's the one point that acts like a linear object. But we have some issues. We're trying to find the velocity of the center of mass, right, of each object, but we've got this omega in there, which is related, but, it's going to get in the way. So, a couple substitutions. We know that for rotation, right, the yi is L sine theta, as I showed you earlier. But we also know that for rotation, the speed of the center of mass is the angular velocity times the radius. And if we solve, angular velocity is speed over radius, right, which we can plug in right there and make an equation that looks more like this one. Right? And that's because of what we're looking for. If I had asked this question and said, what is the angular velocity of each object as it reaches the bottom, we might use this substitution and plug it in there, right, to turn it into something we could solve for omega. So we plug yi in here and omega in there, right, and we get this. I'm going to do a couple of things here. I'm going to multiply by 2, because I don't like fractions. So I'm going to multiply by 2, put it over there. Right? And then I squared this and rearranged it a bit. Notice. Right? And I did that for a reason. That reason being that we're trying to solve for VF, right? And I can do that. It's commutative and associative. Multiplication is. I'm going to multiply both sides of this equation by 1 over m. I'm going to multiply this side by 1 over m, which means I got to multiply it here and here. And I'm going to multiply this side by 1 over m. Why am I doing that? I'm going to multiply by 1 over m because I want to arrange it in a way that's going to tell us something special about hoops, discs, and spheres as they roll down this hill. You might remember this little thing that popped up in the last video. It's going to pop up here as well. So, if I multiply this side by 1 over m, the m just ends up here, and it cancels with this m. If I multiply this side by 1 over m, the m's cancel, and we end up with 2gl sine theta. So, multiplied by 1 over m, multiplied by 1 over m. By the way, if this question just asked about a hoop, a disc, or a sphere, not all three of them, right, I might have come back here and just plugged in the rotational inertia for the hoop, the disc, or the sphere at this step when I'm making all these substitutions, and then just done the algebra, right? But again, I'm working generically until I need to put those in, right? So now that I'm here, I'm going to factor out a VF squared from both terms. I also flipped these around, all right? The order, again, addition is commutative. I did that because I just wanted it to look like what we were doing last time. And then divide by this, right, to get VF squared by itself. And then take a square root. It's not pretty, right, but there it is. This is not an equation I want you to memorize, right? I want you to know how to get there. So this is kind of as worked out as we can without putting in the rotational inertia to make it specific to a hoop, a disc, or a sphere. So let's do that now. We know that the rotational inertia of a hoop about a central axis, which is what it rotates around when it's rolling, is mr squared. The rotational inertia of a disc around a central axis is 1/2 mr squared. And the rotational inertia of a solid sphere around a central axis is 2/5 mr squared. If this was an actual AP-ish problem, you're supposed to know the hoop and the disc. They'd have to tell you the sphere. So we plug these in one at a time. So there's the mr squared for the hoop. Notice H for hoop. D for disc, 1/2 mr squared. S for sphere, 2/5 mr squared. And what do you notice? Yeah, you see this? That's why I did the weird 1 over m multiplication to both sides. The mr squareds cancel. That means that any mass or radius hoop will have the same speed at the bottom of the hill. A small hoop, a big hoop. A massive hoop, a hoop made out of lead, right, or a hoop made out of aluminum, right, are going to have the same speed at the bottom. Same thing with discs. Any size, mass, or radius disc, going to have the same speed. Any size, mass, or radius sphere, going to have the same speed. Kind of interesting, right, the way that works out. And it's got to do with all the different places mass and radius works through there. Kind of a little hard to predict without actually, though, doing the physics, right? Whether that's a Newton's laws approach or, as we're doing here, an energy approach. So this leaves us with 2gl, square root of 2gl sine theta over 1 plus 1. 1 plus 1 is 2. Cancels out with that 2. If we plug in 9.8, 2.4, and 35 degrees, right, we get a final speed at the bottom of the hill for the hoop of 3.7 meters per second. For the disc, 1 plus 1/2 is 3/2. 2 over 3/2 is 4/3. Plug in the numbers, 4.2 meters per second. So any disk will go faster than any hoop at the bottom of the hill. And then for the sphere, 1 plus 2/5 is 7/5. 2 over 7/5 is 10/7. Plug in the numbers, 4.4 meters per second. So these two are close, and I'm going to actually show you a demo of this, right? But any sphere should be faster than any disk, which will be faster than any hoop. Now, it does have to do, of course, with the rotational inertia. And the rotational inertia has to do with the organization of the mass. Notice that a hoop, which has the most rotational inertia, has the slowest speed. It's the hardest to change its motion, its rotation. It's rolling, I guess. A disk, which has the middle rotational inertia, has the middle speed, and a sphere, which has the smallest rotational inertia, in other words, which is easiest to speed up, right, to accelerate, has the fastest speed. You might be able to predict that just by thinking of rotational inertias, right? Although to get the numbers, you got to do the physics. Now, part B, we're going to figure out the order the hoop, the disk, and the sphere would have to reach the bottom. In other words, we're going to find the time. Now, if you remember from the last movie, since all of the forces and torques are constant, that means we have uniformly accelerated motion. And since it's uniformly accelerated motion, this is a kinematics equation problem. We know the initial velocity is 0. We know the displacement is L, or 2.4 meters when we get to plug in numbers. And we know the we know the speed of the hoop, final speed of the hoop at the bottom of the hill, the final speed of the disk at the bottom of the hill, and the final speed of the sphere at the bottom of the hill. Now this is a little different, right? It's been very rare that you've done a kinematic equation problem where one of the things that are given are the final speeds. But that's the way it worked out in this case. It's what we could calculate with energy. So we know the initial, the final speeds, and we know the displacement, and we're looking for time. Only one equation just has those. Notice we don't have the acceleration. Can't really get the acceleration from an energy approach unless you do a different kinematic equation. Now, you can't get it directly. That's where the Newton's laws approach comes in. So the second equation, this says displacement is 1/2 times the quantity final plus initial velocity times the time. Now, remember that this is the one that is not on your equation sheet. And I think it isn't because they expect you to just kind of remember that this equation is really just a written out version of displacement is average velocity times time. Right? Because if you take, when something is uniformly accelerating, if you add the initial velocity to the final velocity and divide by 2, you get the middle velocity, right? That is the average because it's uniformly accelerating. If it's not uniformly accelerating, that's why we have to use calculus, right? We don't have these nice equations. So this is average velocity times time is displacement. So the initial velocity is 0. We solve for the time. Simple algebra. We plug in the L. We plug in for the hoop here. Here's its final velocity. You could reduce this with the L on the top and the square root of L on the bottom, but I'm not going to bother. We plug in the numbers. We get 1.31 seconds for the hoop. Plug in the final velocity for the disk. And we get 1.13 seconds. Plug in the final velocity for the sphere. And we get 1.09 seconds. So notice, right, the sphere will beat the disk, will beat the hoop. And that's any sphere would beat any disk, would beat any hoop. Because as you saw earlier, the mass and the radius canceled out of those equations. So that means they did not depend, the final times here did not depend on the mass nor the radius. More it depends on the orientation of that mass, right? Where the mass is with respect to the axis of rotation. In other words, rotational inertia. So I hope you've enjoyed these two different ways to solve this problem. Now, which one would I use? Well, personally, I find energy easier to use. Sometimes they'll try to force you in one direction or another on an AP test. Like, they might ask you to draw a force diagram and then ask you a question. So you're thinking forces. They may do something like ask you a part A, which is about the gravitational potential energy the hoop has at the top of the hill, which gets you thinking energy, right? But when it comes right down to it, if they wanted to know the time for any one of these or all three of them to get to the bottom of the hill, you could do it either way, right? You'll get the exact same answers. So it's kind of your choice. And even if they made you draw a force diagram in part A, you could attack part B with energy if you wanted to. It's whatever you're most comfortable with and really whatever you can get done the fastest. So they might have a preferred solution, but the rubric will always have alternate solution, right? Or if there's any other way to figure it out, right, it'll be in there. So they'd be okay with that. So a lot of rolling here. Hope you enjoyed it.